In this lecture, we'll be discussing the Laplace transform. The Laplace transform is closely related to the Fourier transform, and it's used in a lot of different places and situations in signal processing. We're going to learn about it here because it's going to give us a powerful tool for analyzing different kinds of systems in order to tell us something about how we can expect that system to behave under different circumstances. So up until now, we've been dealing with complex frequencies that are of the flavor j omega. And if you remember, when we got started with complex frequencies, we did it because we were looking for an alternate way to express cosine of omega t. And as you might remember, we decided that we had e to the j omega times t and e to the minus j omega times t. So just to remind you, we had a complex frequency e to the complex frequency t, and then whenever we had j omega, we're obliged to have its complex conjugate. Okay, we need the complex conjugate there so that the imaginary parts can obliterate each other, and then we're left with the real valued function cosine of omega t. So just to rehash, up until now we've been dealing with complex frequencies j omega, which are in this case purely imaginary. Okay, these are purely imaginary frequencies. But what if we were to expand our definition of frequency a little bit and say we don't want just imaginary frequencies, but we actually want complex frequencies? So what if we had a complex frequency that had a real part and an imaginary part? Okay, before we just had an imaginary part, now we're going to say what if we had real plus imaginary? Well, if you do that, that's the Laplace transform. Okay? It's taking your signals and expressing them as e to the j st, where s has a real part and an imaginary part. Now, most of the intuition is going to be exactly the same because the transforms are very closely related. In fact, you can think of the Fourier transform as a subset of the Laplace transform, because if you take the Laplace transform and you let the real part sigma equals 0, then what you get is the Fourier transform. Okay, so that's how they're related. So one of the, and again, we're studying this because it's going to give us some very powerful tools to quickly analyze how different systems operate. So let's go ahead and take a moment and introduce the concept of what we call the S-plane, which is really nothing more than a complex space, a two-dimensional complex space, and that's going to represent the S variable. So you can imagine that we're going to have a positive real axis, a positive imaginary axis, a negative real axis, and a negative imaginary axis. Okay? And then different systems, what we're going to discover, operate in different places on this S-plane. Now, before I go on, I want to remind you that we just said a moment ago that if you take the Laplace transform and you let sigma equal 0, you get the Fourier transform. And in the case of the plot, that corresponds to the j omega axis, or the y-axis. So in other words, the y-axis, if you just restrict yourself to the y-axis, that's the Fourier transform. And if you do the full S-plane, that's the Laplace transform. Okay, so the Laplace transform is useful, like I said, because it lets us analyze systems, and the Fourier transform is useful because it helps us understand how systems respond to different cosine inputs. Okay, so what we're going to do is we're going to use this tool. We're going to look at the full S-plane, and then we're going to use it to quickly derive some intuition about what's going on the y-axis so that we understand how the system treats different cosine inputs. So the last thing I'd like to do is to talk a little bit about what it means to have a complex frequency, a fully complex frequency, not just an imaginary frequency. So instead of having e to the j omega t and e to the negative j omega t, what if we had e to the st and e to the s conjugate t? Okay, so let's examine that and see what happens. So if we expand, we have e to the sigma plus j omega t plus e to the, now we need s conjugate. Conjugates have the same real part, but the opposite imaginary part. And then we're going to distribute e to the sigma t times e to the j omega t plus e to the sigma t times e to the negative j omega t. And then finally we can factor out an e to the sigma t from both terms, and what we have left is e to the j omega t plus e to the negative j omega t, which is in fact cosine of omega t. I know there's a 1/2 that's supposed to be in there, but that's just a scale factor. Let's not worry about that for now. So if we were to plot this, let's think about what that function would look like. So what we have is a cosine, and that cosine, instead of having a constant amplitude, it's going to have an amplitude that's a complex exponential. Let's see if I can draw that reasonably well. So let me just pencil this in. So this is a complex exponential envelope, and in this case I'm drawing a decaying exponential. So you can think of this term as e to the minus t over some time constant. Okay, it's a decaying exponential. And so that's the envelope, and then you can think of this as a cosine, and that cosine is going to have some frequency. So what I want you to realize is that when we're dealing with something like the Laplace transform, we have S. S has sigma plus j omega. Now, as we've just pointed out, the complex part of S, or rather I should say the imaginary part of S, the imaginary part of S is j omega, and that sets the oscillation frequency. The real part of S is sigma, and that sets the decay rate. In fact, we can see that if we let sigma equal 1 over negative 1 over tau, that's how we get from sigma to the time constant. So in other words, if you know sigma, you can calculate the time constant. It's basically a trivial calculation. Okay, so that's the time constant. And remember, it always takes about 5 time constants for a signal to decay. Finally, let's look at an important detail. I've drawn this as a decaying exponential. Okay, we will always get a decaying exponential as long as sigma is negative. As long as sigma is negative, we'll have a positive time constant, and that will give us a decaying exponential. And generally speaking, that's a desirable quality, is to have a decaying exponential. That describes a system that's stable. So if you imagine jumping on a trampoline, let's say you did one big jump, okay, and then you just sort of landed and waited to see what happened. You would imagine that the trampoline would wobble for a little while, but eventually would just stop wiggling. Okay, that's an example of a decaying exponential. Eventually all the energy that you put into the system decays away and it's stable. On the other hand, if you have a value of sigma that's positive, then instead of having an envelope to this signal that decays to 0, it'll actually blow up to infinity. And that is unstable. Unstable envelope goes to infinity. That would be roughly the equivalent of jumping on a trampoline once, and then instead of stopping moving eventually, the trampoline would just keep bouncing you higher and higher into the air until you flew off to infinity. Okay, so generally speaking, we desire to have systems whose values of sigma are negative because they give us stable performance. And we don't desire to have systems whose value of sigma is positive because that tends to be correlated with unstable performance.